So in our last lesson, we learned about how we can determine if a function is increasing or decreasing at a point, and if it's concave up or concave down at a point, basically by looking at values of the first derivative or the second derivative. In this review lesson, we're going to be sort of extending that into entire intervals. But before we get started, let's take a deep breath. And let's begin. So I'm really going to try and approach this lesson from a slightly different direction than I did when I taught it last year. And I want us to understand that there's sort of this key point that when we're trying to analyze a function, it can be helpful to sort of split the domain up into smaller subintervals and find out what happens on each of those subintervals. And the most common way to do that, to define these subintervals, the most common way to do that is by setting the function or its derivatives equal to 0 and then solving. Okay? And I want to point out before we get into examples, and this video is going to be almost entirely just examples of us doing this. Given a function y equals f of x, there's basically three things that we can investigate using what we currently know about calculus. Okay? We can analyze whether the function is above or below the x-axis by analyzing the function itself. We can determine whether the function is increasing or decreasing on an interval by analyzing the first derivative. And we can determine whether a function is concave up or concave down by analyzing the second derivative. So depending on whether a question is asking about increasing or decreasing, or concave up or concave down, or whether it's above or below the x-axis, that sort of lets you know which of these functions you should be analyzing. But the process we're going to use to do the analysis is going to be the same across all of them. So we're going to do an example of that, and then I'll detail the method, and then we'll get into a few more examples. And, actually, before I get into this, I want to point out to you that most all things in this class benefit from us giving our work space and being organized about what we do. I think especially with these ones, these are not the kind of problems that you want to try and cram all of your work into a small space. So I tried in the guided note frame to give sort of quite a bit of room for you guys to be able to really, really write out all the things that you need to. So sort of keep that in mind. Get yourself mentally ready to spend space developing these intervals and showing and doing this analysis. So in this first example, we're being asked to determine the interval or intervals on which the function f of x equals e to the x minus x is increasing. So I think the first thing that I might ask you guys is, how do we determine if a function is increasing? What does it mean if f is increasing? Another way we could say that is that f prime is positive. And so what that lets us know is it means we want to do our analysis of f prime. Okay, so again, I'm going to go through this example. Right after this, I'm going to sort of talk in detail about what the method was that we will have just done, and then we'll get on to other examples. So if I want to analyze the derivative, what I'm going to do is I'm going to take the derivative, f prime of x. The derivative of this thing, well, the derivative of e to the x is just e to the x. The derivative of x is 1, so e to the x minus 1. And then in order to analyze this thing, in order to break it into intervals, I want to set this equal to 0. I want to find out where is the derivative 0 so that I can use that to split up the domain of the function. So if I do 0 equals e to the x minus 1, means I get e to the x equals 1. And we can change forms here. This would be the natural log of 1 equals x, or you can just sort of solve this and see this is going to be x equals 0. Okay? Now, what is the domain of this function? What am I allowed to plug into this thing? Does it have any asymptotes or any holes? No, it doesn't. The default domain of this thing is all real numbers. In other words, everything from negative infinity to positive infinity. But now that I know that the derivative is 0 when x equals 0, it means that I'm going to take this domain and I'm going to split it up into two subdomains. I'm going to have one of them that goes from negative infinity to 0, and then another one that goes from 0 on toward infinity. So you can almost imagine that this is like a giant number line, right? That's going from negative infinity over to positive infinity. And at 0, something changes. And so what I'm going to do over here is I'm going to analyze what happens from negative infinity to 0, and over here I'm going to analyze what happens from 0 to infinity. And so now all I really have to do, and hopefully you remember from last year, I just need to choose a representative value. I need to pick any number that I want between negative infinity and 0 but this is an open interval, so I can't pick negative infinity and I can't pick 0. So the easiest thing to pick is probably like -1. So I'm going to analyze really quickly, what is f prime of -1? Well, f prime was e to the x minus 1, so this would be e to the -1 minus 1. That's 1 over e minus 1. And here's the really important part. You don't need to know what this number is. All you need to know is whether it's positive or negative. Well, e is bigger than 1. It's like 2.7-ish. So 1 divided by that, that's definitely going to be less than 1. Something smaller than 1, some decimal minus 1, this is going to be something negative. So that means I can tell here that f prime, the derivative, will be negative on this whole interval. And so you can see here that I wrote a quick bit of reasoning there. I wrote, the derivative will be negative on this interval, so the function will be decreasing on this interval. Okay? Now I'm going to go over and do the exact same thing over on the other side. Over on the other side, I'm going to pick another representative. I'm going to pick 1 from this interval. F prime of 1 would be e to the 1 minus 1. This is e minus 1. That's really clearly positive. And so now I can write a really similar statement over here about how, sort of like really similar to this one. So pause the video, make sure that you can write sort of what that thing would be, and then we'll check in. And so I think the last thing that we should do here after writing a statement like this, like, f prime is positive on the interval, so the function will be increasing on this interval, we want to answer the question. The intervals on which the function is increasing, this function is increasing on the interval from 0 to infinity. And so, your answer to this problem, your answer is the interval from 0 to infinity. This is the process that we're going to use to do this interval-based analysis. So now that we've sort of seen this method in action, I wanted to detail what the steps are for you. So it's already been provided for you on the note frame. This is just kind of your opportunity to sort of annotate these as we're going along. So if any of these steps really jump out at you, or if there's something that I say here that's important, underline, annotate this. So the steps that we use. Step number 1, we determine the domain of the function. And this one is one that people often skip over and don't. To determine the domain of the function, if the function has any holes or any asymptotes or like discontinuities, any like breaks in the function, those are going to actually generate more subintervals. Okay. The second step is that you want to set the function you want to analyze, whether it's the original function or whether it's the derivative or the second derivative. Set that function equal to 0 and solve. Okay. Find the zeros. Okay. Step 3, you're then going to actually split the domain of the function up into subintervals using those x values that you found in steps 1 and 2. The example that I just didn't have any holes or asymptotes, so we just used the 0 that we found from the, step 2, but sometimes we get them from step 1 as well. The next step is that you need to choose a number from each interval and evaluate the function that you're analyzing at that value. And then finally, for each interval, you're going to write a brief statement or analysis of what you found and what that means. And then you repeat that for all the intervals, and then you're done. Like you've completed your analysis. So this is the method we're going to use. We're now going to carry this forward and use it in 3 different examples that are each going to be a little bit different in their own regard. So this example is probably the longest and most challenging example that we're going to go through today. I think I wanted to do that while you more than likely still had a good amount of brain power left. So we're going to do a bunch of different analyses on this, right? We're going to do whether the function is positive or negative, whether the function is increasing or decreasing, and then whether the function is concave up or concave down. And then we're going to try and use all of that information to sketch what this graph looks like, which is kind of exciting because this is not a graph that we would normally expect to be able to come up with without a calculator. So let's dive into this, right? Part A, determine the intervals on which the function is positive or negative. Well, if I want to know if the function is positive or negative, I'm going to start, so what's the domain of this thing? The domain of this thing is everything except the bottom can't be 0, right? So my domain here is, basically x can't be 0, which means that's going to be one of the values that we use in figuring out intervals for this thing, okay? Now the other thing we need to do is we need to look at this function being equal to 0. So when is x squared plus 4 over x equal to 0? Well, if I multiply that over, I'm going to get x squared plus 4 equals 0. That means x squared is negative 4. This has no real solutions. Okay, so since this thing has no real solutions, I don't get any more things that I need to break my intervals up into. So what's the only x value that I need to use to make intervals? Only one I need to use is this one that came up from the domain. Okay, so I'm going to have one interval set up from negative infinity to 0, and then I'll have another interval set up from 0 to infinity. And what am I going to be testing here? If I want to know if the function is positive or negative, and I just set the function equal to 0 right here, it means I'm going to be testing that function. So over here, I'm going to do f of negative 1. And so when I do f of negative 1 here, if I plug it into the original function, I'm going to have negative 1 squared plus 4 over negative 1. We can actually compute exactly what this is. This is negative 5. And I mean, so yay, we found out that the function is negative at this value. That means that the function is going to be negative on this entire interval. And so I'm going to write a statement about that. Now, some of you might be wondering, why, and we covered this last year, but I should review it again here briefly. Why does this thing being negative just at this one value, why does that force it to be negative on this entire infinitely long interval? Well, the reason is, imagine if there was some other place in this interval where it was positive. How would the value have gotten from being negative to being positive? Like if you had a graph of this thing and it was negative somewhere and positive somewhere, if it was going to go from negative to positive, wouldn't it need to hit 0 somewhere? But we just found out that this function is never equal to 0, which means this thing can never cross the x-axis, which means it can never change from negative to positive on this interval. It might be positive over here. It could use this split in the domain to be able to jump up to the other side, but 0 is the only place that change can happen. And so when we found this was negative, it forces everything on this interval to be negative. All right, this is a long problem. Let's keep going. I need to test something over here. Let's do f of positive 1. That'd be 1 squared plus 4 over 1. This is positive 5. Well, great. We just found that f of x is going to be positive on this whole interval. And great, at this point we've answered part A. Part A is that this function is positive. Oh, I'm sorry, determine the intervals on which it's positive or negative. So it's positive on the interval from 0 to infinity. And it's negative on the interval from negative infinity to 0. So we've answered part A. Yay! Now we're going to move on to part B. They're now asking, what about intervals where our function is increasing or decreasing? I want to move this up over here to the side so I've sort of got more room to work with here. So there we go. If I want to know where the function is increasing or decreasing, that means I need to analyze now the first derivative. Okay, so in part B of this, let me go to a different color here. In part B, I'm going to need to start by figuring out what is the derivative. Okay, the derivative of my function, so I'm going to need to use the quotient rule here. So low d high x times, x times 2x, low d high, minus high x squared plus 4 d low 1 square the bottom x squared. So let's hear f prime of x is 2x squared minus x squared minus 4 all over x squared. This looks like I'm going to get f prime of x is x squared minus 4 over x squared. Great, so that's my derivative. Okay. Is there anywhere that this derivative is not defined? Yeah, it's not defined. X can't be 0, just like before. Right? X can't be 0 here. Is it possible that this derivative is equal to 0? Well, yeah, if I wanted to look at where this thing was 0, I'd multiply the x squared over. I'd get 0 equals x squared minus 4. And this is basically going to have solutions plus or minus 2. So now using our method from the previous slide, I've got 3 values that I need to use for intervals here. I've got 0, positive 2, and negative 2. All right, so I'm going to go here and I'm going to set up these intervals. Actually want to erase some of this so that I can sort of work, all in a line right here. So one of my intervals is going to go from -infinity to -2. The next would go from -2 to 0. The next would go from 0 to 2, and the last would go from 2 to infinity. And remember, what do I need to do on each of these intervals? On each of these intervals, I need to plug in some representative value into the derivative and find out if the derivative is positive or negative, and then write a little statement for it. I'm going to pause the video and go through that now. I'm going to try and go through it fairly quickly here just so that this example doesn't go on for 20 minutes alone. So let's see here. For here, I'm going to pick the representative -3, so f prime of -3. When I plug that in, I'm going to get 9 minus 4 over 9, which is clearly positive. And so I'm going to write my little statement here about that. Okay, going on to the next interval, I'm going to choose the representative -1. Remember, it doesn't matter what you choose in there, but anything else would be a decimal, and I don't want to deal with that. So f prime of -1, plugging that again into the derivative, that's going to give me 1 minus 4 over 1. This is clearly negative, and so I'm going to write a really similar statement here. Continuing on, I'm going to do f prime of 1 here. That's actually going to be really similar to the other one, 1 minus 4 over 1. This is, again, negative, and so because the derivative is negative, the function is going to be decreasing this interval. All right, so I went ahead and sort of quick finished this one over here. This part is really, really similar to this one. I just chose positive 3, plugged it in, found the derivative was positive, which means the function is going to be increasing over here. Continuing on to part C. In order to do part C, I'm going to need to use the second derivative, right? So the first thing that I need to do here is I need to take the second derivative. So I'm going to go back and remember what the first derivative is. I'll need to use the quotient rule again. Fortunately, it's not too bad. So this is going to be low d high minus high d low square the bottom. Now, when I actually go through and simplify this, this piece right here is 2x cubed, and then this is going to be minus 2x cubed. So those are actually going to drop out. All that's going to be left up here is 8x, just the 2x times the 4. So we'll have 8x over x to the 4th, which is actually going to simplify down to 8 over x cubed. Now remember, what do I need to do with this thing? First, I need to figure out, is it defined everywhere? And you'll notice that it's not. This thing can't be 0. So I'm sorry, the denominator can't be 0, so that means x can't be 0. Is it possible for the second derivative to actually equal 0? And the answer here is no. If you try and solve this thing, if you try to do 8 over x cubed equals 0, when you multiply the x cubed over, you get 8 equals 0, which means there are no solutions. So good news, we don't need to do 4 intervals again. I'm just going to need to do the 2 intervals based on the one value here of 0. So I'm going to do this thing again where I sort of like shrink this stuff down and move it up here again. Because ultimately I want to be able to see all the stuff in the same place so we can use it for the graph. So intervals here. I've got one interval that's going to go from -infinity to 0, and one interval that's going to go from 0 to infinity. Okay? And remember, now I'm testing the second derivative because I want to know about concavity. So I'm going to do the second derivative evaluated at -1. Well, my second derivative was right over here, right? It was this 8 over x cubed. So when I plug in -1, I get 8 over -1. This is really clearly negative. And so I'm going to write a statement about that. Because the second derivative is negative, what does that tell me about concavity? So what I wrote here was that the second derivative is negative. That means that the derivative is decreasing. And by definition, that means that the function is concave down in this interval. And that's what they were asking for in part C. They were asking about concavity. For this other one, very, very similar. The second derivative at +1 is 8 over +1. And so now I'm going to write a really similar statement here about the second derivative being positive. All right, there we go. So we finished parts A, B, and C. We found places where the function was positive and negative. We found places where the function was increasing and decreasing. And finally, we found places where the function was concave up and concave down. So now what we're going to do is we're going to try and take all of this information and we're going to try and put it all into understanding the graph of this function. Okay, so the thing we found out in part A was that the function was going to be negative between negative infinity and 0. So the function is going to be negative over here. And we found that between 0 and positive infinity, my function was going to be positive. So it means when I graph this thing, like this part of the function is all going to be down here, and this part of the function is all going to be up here. That's what it means for the function to be negative here and positive here. Let's keep going. What did we learn about the derivative? When we did part B, which was all up here in blue, we found that my function was going to be increasing between negative infinity and negative 2, and again between 2 and infinity. So now I can sort of come back and go, all right, well, something's going to happen here at negative 2, and something's going to happen over here at positive 2. Sorry that I'm going to write over my writing here a little bit, but I sort of want to put, well, maybe I can do it up here. Between negative 2 and infinity, my function needs to be increasing, and between 2 and infinity, my function needs to be increasing. And then between negative 2 and 0, and between 0 and 2, my function needs to be decreasing on both of these. Okay? The final thing I'm going to do is I'm going to go back and look at what we found out in green. In part C, we found that from negative infinity over to 0, my function is supposed to be concave down. Concave down. And between 0 and infinity, my function is supposed to be concave up. All right, so now that I've got all of this information, I want to go through and try and make sense of what this graph is going to look like. So here we go. We remember that it's supposed to be negative here. So the negative part means it's all going to be down here. On this section here, it's supposed to be increasing but concave down. Increasing but concave down means it's going to be like this, right? So I'm going to draw my graph that it's going to be like this. Okay. On the next segment, it's supposed to be decreasing and concave down. And this is supposed to be an asymptote. All right, so this thing is going to decrease and concave down like that. Wonderful. As I move on, over here, it's supposed to be decreasing, it's supposed to be positive, so my whole graph's supposed to be up here. There's an asymptote, it's supposed to be decreasing and concave up. So decreasing but concave, so it's supposed to be like this. Oh, so you can sort of infer this thing is like coming down from the asymptote, and it's like a leveling out here. And then over here, it's supposed to be increasing and concave up. Increasing and concave up means it's going to be doing something like this. And so I get that my graph is going to look like that. Now, I get it. This took us 14 minutes to do. Like I said, this is a long problem and there were complicated derivatives. I've got 2 more examples and they're both going to be much less sort of like cumbersome than all of this was. So I hope that made sense. If you have questions about this, please like write them down, ask them, like, make sure that you let me know about that because this is an important skill that we need to develop to move forward into other things. All right, so like I said, this one should be more straightforward than the last one was. It's a polynomial, so the derivative is going to be easier. So part A, determine the intervals on which the function is increasing and decreasing. So go ahead and pause the video, go through the process we did in the last one, and then come back and check with me on part A. So part A, I need to start by taking the derivative. The derivative of this thing is 6x squared minus 18x minus 24. I now need to set this thing equal to 0. So 0 equals, and it looks like I can factor that. I could factor out the 6, x squared minus 3x minus 4. And then that thing even can factor. This would get me 6 times x minus 4, x plus 1. So it looks like my values here are 4 and negative 1. So those are going to be the things that I use to set up my intervals. So I'll get one interval that goes from negative infinity to negative 1, one that goes from negative 1 to 4, and one that goes from 4 to infinity. Okay? Now all I need to do is I need to take these values and I need to plug them into the derivative. Okay? Now there's sort of an interesting thing we can do here, right? This is the derivative, but it might actually be easier to use the factored form of the derivative. All right, because check this out. If I decide to do like f prime of negative 2, I could plug that into this thing, but it's actually really fast if I do, so watch this. I'm going to do 6 times, when I plug negative 2 into this, negative 6 times negative 1. And you can tell right there that this is positive. right? I can see here that the derivative is positive. That means the function is increasing. All right, let's do a really similar thing on this next one. I'm going to use 0 as my representative here. F prime of 0 is going to be 6 times negative 4 times 1. That's clearly negative, and so I'm going to write a statement here about that. And then finally, for my last interval, I'm going to choose 5 as my representative here. So f prime of 5 is 6 times 1 times 6. Important thing here is that this is greater than 0, that this is positive, and so I'll write a statement about that. Great, so at this point we're done with part A. We're going to move on to part B, where I need to do effectively the same process for concave up and concave down. Right? So, yay, we sort of mark off that we finished this work here. I'm going to move to a different color. First thing I need to do here is take the second derivative. So take this thing and take the derivative. F double prime of x is going to be 12x minus 18. This looks like it's going to be really, really easy. If I do 12x minus 18 equals 0, the only thing I have is 3 halves. So the two intervals I need to set up are from negative infinity to 3 halves, and then from 3 halves to positive infinity. You might notice that I'm skipping that step 0 because there isn't anywhere that this function is undefined. This function has a domain of all real numbers. Here I need to test my second derivative. So if you haven't already done this, pause and try it on your own. My representative here, I'm going to use 0. The second derivative at 0 is, well, if I just plug it in here, it's negative 18. And I'm going to write a statement about that, but I want to do this one over here first. The second derivative here, I guess I should plug in like 2. That looks like my best choice. Plugging in 2 to this is going to get me 24 minus 18, which is positive 6. Great, so that's positive. So again, I can sort of write my statements underneath for my analysis. All right, so I've got my analysis. I can see where this thing is concave down and where it's concave up. Now we want to move into part C. It says, using the y-intercept of f of x as a reference point, sketch the graph of y equals f of x. Right? So I'm going to make some more room for myself here. So let's see, when I go to sketch the graph of this thing, what is the y-intercept of this graph? Hopefully you can tell that really clearly. The y-intercept of this graph is 5. So there we go, 5. I know that there's a point here. And what do I know about these other things? We knew that something kind of special happened back here at negative 1, and something happened over here at 4. That was in the first derivative, right? So between negative infinity and negative 1, my function was supposed to be increasing. And from 4 to infinity, it was supposed to be increasing. And then between negative 1 and 4, it was supposed to be decreasing. And then we did our concavity stuff in blue, right? So something special happened here at 3 halves, 1.5, right? And we knew that from negative infinity to 3 halves, my graph was going to be concave down. And then from 3 halves over to infinity, we went back to being concave up. Okay? And so now we can sort of, I like to start with the point. It's, starting with this reference point, this 5 here. This thing is in a region that's concave down. It's sort of in this region right here where it's supposed to be concave down and decreasing. So something like this. Right? So concave down and decreasing. All right? And then in this region right in here, it's supposed to be concave up and decreasing. So decreasing, but concave up. Over here, it's supposed to be concave up and increasing. So this is sort of like the smiley face increasing thing. Finally, I've got this last region back here where it's supposed to be concave down, but increasing. So increasing, but concave down. Yeah, there we go. Right on. This is my sketch of what this graph is going to look like. And it's not surprising. This was a positive x cubed style graph. It makes sense that we would get something like this. All right, we made it. I've got one more example for you, and it's actually going to be really quick because it's a conceptual thing. So let's take a look at this last one. These last ones can be confusing. We'll do more practice with them, but I wanted to get us a chance to see this here. So here I'm giving you a graph, and I want you to notice this is the graph of the derivative. So I'm giving you a graph of the derivative, and my first question is, where is f of x decreasing? Not where is the derivative decreasing, where is the function decreasing? Well, a function is decreasing when the derivative is what? When the derivative is negative. Well, you happen to have a picture right here of the derivative. Can you tell where this function is negative? Isn't it negative between -4 and 2? So the function is decreasing between -4 and 2. That's the answer for part A. Okay. For part B, B asks, where's my function concave up? Well, concave up means that the second derivative is positive, but the second derivative being positive means that the first derivative must have been increasing. Well, you happen to have a picture of the derivative right here. Where is this derivative increasing? Isn't it increasing right there? So in other words, from -1 onward? Great, so from -1 to infinity. That's where our function is going to be concave up. Like I said, we'll get some more practice with this in the assignment for today, and it's something that we'll come back to and see at some point in the future. But I wanted to make sure that this idea of thinking about things on intervals can also be applied to sort of a graphical understanding. So as always, I hope that made sense. If you've got questions, please ask me. Please let me know. And best of luck as you work through the assignment and the practice for this.